Hey guys, welcome back to Genius Learning. So I want to look at a Physics 1 problem dealing with circular motion or an arc and friction along a horizontal surface. And we want to solve this using conservation of energy. Okay, so we have this box or this package that starts off at the top of this ramp at A, and it moves through this circular arc of radius R. It comes down to B, right, and then slides 3 meters all the way until it stops at C. Okay, and so velocity C is equal to 0, and then what we're given is the mass of the box, the radius of this piece right here, which is the same thing as this and that. So this is like a perfect circle over here, a quarter circle. And so then we start at A, initial velocity is 0, so we start at rest, and then we slide down, and then we slide for 3 meters. And then the velocity at B, so when we slide down and we pass this point, we're at 4.80 meters per second, right here. And then we slide 3 meters this way. And so we want to know first the friction on the horizontal surface. So from here to here, how much friction was there if we stopped at 3 meters going 4.8 meters per second when we started? Okay, so let's use conservation of energy. All right, so we have initial kinetic energy plus initial potential energy, right, plus work done by friction, okay, equals kinetic energy final plus potential energy final. Okay, so we're always going to put plus work, but just make sure you understand that if the friction is opposing the motion, we're negative. Okay, and so let's see what we get for this part. Okay, so for work, all right, we have the definition is going to be force dotted with displacement. All right, and since we're horizontal, right, there should be a cosine of theta here, but since the angle is 0, cosine of 0 is just 1. So we could just use this regular formula here. The only force that we're feeling, right, is going to be mu, right, which is the force of friction, times mg, and then the horizontal displacement d. Okay, so that's going to be our expression for work. And since we're going to say that in this direction we're positive x, and then opposite to that is negative x, right, then this is also going to be negative because it's opposing the motion as it slides. So in full, we have the initial kinetic energy, so we have 1/2 mv at A squared. Then we have plus the potential mgh at A. So this is the height at A, and this is the velocity at A. Okay, and then we have minus, okay, oh, all right, so sorry, these should be B. Okay, so let me correct that here. So the velocity at B, the height at B, because we want friction on the horizontal surface. Okay, so we're actually starting right here. Okay, so the initial kinetic energy is going to be 1/2 velocity at B, right? And then the initial potential energy here is going to be mgh at B, all right? So this is where we're starting because we want friction on the horizontal surface. So this is the only part that's horizontal. Okay, so that's the initial part. And then we got minus, right, mu mgd for this part, for the work, right, opposing the motion. And then on the other side, we're going to have kinetic energy final. So 1/2 mvc squared. So the final velocity is going to be here at C. We're going on the horizontal from B to C. And then finally the potential energy plus mg and the height at C. Okay, so now that we have all this, let's look at what we can cancel out. All right, we know that the velocity at B, we have 4.80, and we know that the height at B is 0, it's on the ground. Okay, so that's the first thing we can cancel out. We have all these values, gravity, we have mass, we have displacement, that's fine. The velocity at C, it comes to a stop. So we know this is 0, and also the height at C, right? The height, this is also on the ground, C, so there is no height. So now that leaves us just with this term here and this term here. Okay, so let's put it together and we'll solve for mu. So let's first, okay, this is mu k. So first we're gonna do this piece here. Let's move it to the other side of the equal sign. So we're gonna be left with this, which is minus mu k mgd equals, if I put this on the other side, it's gonna be minus 1/2 mvb squared. Okay, and then I can just get rid of these minuses. Okay, and then I'm going to divide mgd onto this side, and then finally I'm going to get mu k is equal to 1/2, all right, m, which is going to be 0.2, velocity at B, which is going to be 4.80 squared, right? And I'm dividing this to the other side on the bottom. So I'm dividing this. So we're gonna have m, which is 0.2. I'm gonna have g, which is 9.8. And then I'm gonna have d, which is just 3. Is it 3? Yeah, it's 3. Okay, so at 3. All right, so putting this in your calculator, and we should get, okay, we should get mu k is equal to 0.392. Okay, so let's box that up. So there's the friction on the horizontal surface. So that's the friction right here. Okay, so along this path, this box is just sliding and slowing down, and it's slowing down. This is the coefficient of friction, and because this is the coefficient of friction, it only allows it to slide 3 meters per second, 3 meters, right? Starting off with 4.8 meters per second. All right, so now let's look at B. Okay, so let me separate this a little bit. So the work done on the box by friction through the circular arc. So the work done on this box by friction. So what is friction doing to this box as it slides through this curve right here? Okay, and let's find out. So again, we're going to use conservation of energy. So we want to do kinetic energy initial, and this time it's at A. So we're starting from here and we're going here because we want to know through the circular arc. Okay, so from A to B. So we're starting at kinetic energy initial at A plus potential energy A, okay, plus work. Remember, we're always going to write plus work, but we got to figure out if it's going to be negative or not. And then we have kinetic energy final, which is at B, plus potential energy final, which is also at B. Okay, so let's box this up. And now let's see what we got. So for this problem, we're actually solving for work, right? And so we don't need to express it in any form. This is exactly how we need to have it. So let's see what we have that we can cancel out. So we have kinetic energy initial. So let's do 1/2 mv at A squared plus mg height at A plus work due to friction equals the 1/2 mv squared at B and mgh at B. All right, so what do we know? We know that the velocity initial at A is 0 because we started at 0, right? The height at A is all the way up here. So if this line is extended like that, what is this height right here? That's what this HA is all about. And so if you see that this H is the same thing as this height, right? And this is a quarter of a circle. So like the R doesn't change. This R is the same thing if you were to put it right there. It would be the same thing as if you would put it right here. So these are all the same length. This one, this one, this one. So this R is the same thing as this H. So R is equal to H. So here we're gonna change that, okay? Before we do that, let's look over here. Velocity at B, it was given to us. And here at height B is 0 because we start on the ground. Okay, so some of those things canceled out. Now let's take a look at the rest. I'm gonna rewrite this. Let's see what terms got left behind. This term, and this one. So HA, I'm gonna write mgr because HA, right, is equal to R. Then I'm gonna write plus work due to friction is equal to 1/2 mvb squared. All right, so let's solve for work. So we want to put this on the other side by subtracting it. So we have work due to friction is going to be 1/2. This right here is going to be 0.2 for the mass. The velocity at B is 4.80 squared. And then remember that we wanted this on the other side. So we're going to subtract, right? Now we have M, which is 0.2. We have G, which is 9.8. And we have R, which I'm going to write here, is 1.6. Okay, so that's a 1.6 in there for our radius. And that's it. So now let's put all this in the calculator. And we're going to see that our work due to friction, okay, done by friction on the box, is going to be negative 0.83. Okay. So it makes sense because the work done on the box by friction is going downward, which is, you know, positive, and friction is going to be towards the left, or in this case up the ramp. And so it makes sense that the work done by the box or done by friction to the box is negative. Okay, so that's how we find that. And if you guys found this helpful, please subscribe and comment below to see any other problems that you guys might want to have examples to.